another draft physics video production. You're probably over here. Probably. Anyway, let's play some of this and then I'll throw in my context. 3 minutes on, why microwaves microwave. And it's probably not nearly enough stated. But anyway, let's play along.
Look at what photons are in terms of how they work inside microwave ovens. Now, microwave ovens heat up our food, and most of it...
Oh, that's annoying.
Your business idea needs a website?
Really
so go to
annoying.
Wix.com. What are you waiting for? Today's the day.
Special K knows only real
Shit.
strawberries taste this good.
Fuck.
You can't fake delicious.
of us are familiar with what they are. And let's say here we have a chicken heating up, and the reason why food heats up in a microwave oven is because the energy that's being imparted on the food by the microwave oven is of the exact correct frequency to interact with the water molecules inside the food.
All right, so it's really not the exact frequency. I mean, that's really saying it too extremely, I would argue. It's within a range, and they really should go into the chemistry of water, I mean, frankly, to describe this more accurately. But obviously these water molecules are what are primarily excited by the microwave oven in terms of the most of the stuff that's going to be able to gain momentum in some meaningful way is smaller molecules like water. And big giant proteins and stuff aren't going to be able to get aren't going to be moving around as much, aren't going to be as effective in absorbing energy of any form. Well, any form is the wrong way to say it, but anyway, so we already know something. Water tends to do this. It likes to be in clumps, and what's basically happening in a microwave that somehow it's turning into little clumps. They're not necessarily going anywhere, but it's just breaking apart, fracturing, and the hotter you get it, the more smaller little groups of atoms you break it into. I mean, it likes to stick to itself. So that's the idea, is that any bit of water will just become part of the water Borg. It always wants to make a Borg. So whatever. And the point is, when it's a gas, it's still little Borgs, but there's very small Borgs. And when it's a liquid, they're bigger Borgs. And when it's a solid, then the Borgs get into an arrangement where they become another Borg, in the sense that they're all probably lined up in a circle, all the Borgs, and that would be the solid form. So anyway, all you're really doing is you're just breaking the arrangement by hitting the molecules with energy. And the key to the thing is if the thing was like it was just dominoes, all right, you could sort of understand. Let's say they're round, pillars like dominoes, and you can hit them, and if they just bump into each other, then the energy just pops out here and then goes back, and everything relaxes again, and there's no problem. So that's transmitting. And what's just happening when it's sensitive to a certain frequency, it just means that the frequency comes in at a rate. If it's getting bombarded at a specific rate, that rate's faster than, say, the rebound of this domino, the time it takes the domino to go back up, let's say, and so it's pushing against the push. And so that ends up being like, if I had two things and I take it, put it in here. If I was to try to bang two things together, you could sort of understand that if there was pressure that built up between them, like I say, this thing plows into this thing. Well, if this back pressure is too high, that's going to create a tendency to move the momentum in another direction. So this thing will go this way and this thing will go this way. And so it's when you disperse the heat into these other dimensions, up and down and out and in. So that's sort of what you always have to think in the context of, is that you can't see that. I got room down here. Is this stupid three-dimensional thing? Okay, so you're moving something in one dimension, and when you're heating something essentially, and it's not the energy staying in the thing, well, that just sort of means that you've ended up pushing that momentum into one of these other dimensions, and now it's going to be a lot harder to balance this energy because it's moving in a dimension, these other dimensions, and so now it's moving stuff in all kinds of other ways that you're not going to be able to balance it with some other. It's not as easy to balance the energy. That is to have two things. I mean, ideally, what's going to slow things down is to have two things that are moving into each other, two big things, because what they will do is cause balance, and they'll just both stop. That's what's going to actually happen with the big things, in terms of they'll sort of restore the balance. The motion of the one thing will be undone by the motion of the other to both stop. All right. So anyway, that's sort of a context, sort of. The point is dispersion. So at certain frequencies, the energy won't go tip through. It'll end up going sideways. And once it starts going sideways, it goes in all kinds of directions. And now it's going to be a while before you can have the two bits of energy hit each other head on and cancel. Now, I'm not saying the fundamental energy cancels. Just saying once you have motion in big things, it sort of does cancel.
Now, it turns out water molecules are polar molecules. You can see that they tend to be positively charged on one side and negatively charged on the other side. So when photons of the microwave, in this case microwave photons, enter the food.
I really hate that. Anyway, it's obviously not doing it. It's push. And it's the speed of the push that matters. It's momentum, simple. It's not momentum this way and this way. It's this way and this way. It's momentum, it's straight ahead into the speed of light. And the other part they sort of screw up is when they talk about molecules and them being imbalanced, like having two hydrogen and an oxygen. What they can't account for is the fact that those molecules can rotate in lots of different ways, based on the fact that the hydrogen atoms will absorb energy at a different rate. That is, a different frequency will disturb them than the oxygen one, for example. So then the little water molecule can tend to start to move and rotate. You can actually spin one probably, and that makes it so they start to fall apart. And so you can sort of understand some of this stuff too by just other experiments, like water, distilled water, pure water, doesn't boil at the same temperature, much higher temperature. I don't know if it boils at all, because you won't. You need the impurities in there to make the water molecules really start to turn into tiny little droplets. Because when they bang into each other, they tend to want to absorb each other. And you can sort of see that in space when they put water droplets in the space shuttle or something, and they just do that. You can just see the energy inside of them moving from one side to the other, and they just bulge out on one side, and they bulge out on the other side, and the energy just stays inside. And that's what it tends to want to do. But if you put an impurity in there, then the water smashes against something else, and it breaks off into much smaller pieces going in all kinds of directions.
They will ultimately cause forces to exist in one direction for the positive charges and the other direction for negative charges, and then as they alternate, because of course the direction of the electric and magnetic field inside of photons change with the frequency of the photon, you can see that the forces that...
So again, this just goes back to their standard model, the fact that they made a decision 100 years ago about how they're going to diagram what an atom is, and instead of making it something held together by magnetism, in the strict sense where magnets have positions, they've made this rotating, spinning electron thing that was totally unnecessary. They made atoms look like solar systems, and it was just a huge mistake.
Alternate, and that the objects then begin to oscillate like this. So instead of course, absorbing it by simply causing some internal vibration to exist, what happens is that the molecule begins to vibrate back and forth like this.
Right, which would be fine if it was capable of vibrating with its neighbors. So if they all vibrate, if they all turned, and the other one turns next to it, and the other one turns next to it, well, no problem. It'll just transmit the energy out to the outside world by essentially expanding its surface, and letting the outside world push it back in, and to compensate for the energy, and so everything will restore to its original position. But as soon as the energy starts going sideways, that is, as soon as you push too hard, you squish things out sideways, and that's when the heat's going to be there a while.
And that's how it absorbs energy, and that's why the heating process takes place. The kind of process that takes place here is what we call dielectric heating. That's the effect that it has. The microwaves, photons, they have a penetrating ability of about 25 to 38 millimeters, which is about 1 to 1.5 inches. So when trying to heat up a big clump of food,
Right, and that just has to do with the average density of the gun. So obviously if you increase the strength of the microwave gun, you'll probably get a little deeper, but then the mass of the material is going to make a difference and all that kind of stuff. So you're just saying how what's the kill rate of the force you're putting in, but you could argue that's true for everything. I mean, every surface, depending on its density, more the light goes deeper into it when it reflects.
it doesn't work very well because the microwaves cannot get to the inside of the food. They will tend to eat the outside layer of the food, and then the heat will slowly transfer to the inside, and that takes a little bit longer. Now, the frequency at which the...
Right, well, yeah, but it was probably more effective. But again, it's just a dispersion. You gotta, once you start getting things moving in the other two dimensions, then it's going to take a while before you'll have your head-on collisions that undo your motion. You're just trying to undo motion.
water molecules will vibrate back and forth inside food is 2.45 gigahertz. So what kind of wavelengths, microwaves do you need for that to work the best? Because you want the frequency of the microwaves to be in sync with the frequency oscillations of the water molecules inside the food.
Right. So, but these numbers don't really mean anything because what would be ideal to vibrate water molecules might not be ideal in the sense that it's going to make too much noise that'll interfere with a lot of other stuff. So they pick a frequency that moves the water molecules a lot, but probably not the optimum one. The correct frequency is probably something shorter. I mean, I think they're going to come up with 12 centimeters here, and it's probably 5 that water really likes.
So we use the equation C equals F times lambda, frequency times lambda, to find out the wavelength of the microwaves required to do so. So when we plug in the numbers, we get 3 times 10 to the 8 meters per second for the speed of light divided by the frequency of 2.45 times 10 to the 9 hertz, because giga is 10 to the 9, and now I need the calculator to figure that out. All right, so we have 3e to the 8 divided by 2.45 e to the 9th, and that leaves us with about 12.25, so that lambda equals 12.25 centimeters. So that is the wavelength in a microwave oven that's ideal for heating up food, because that wavelength microwave will have the exact frequency required to impart the energy onto the photon. And how does it do that? The photon comes in, it
does that nonsense again. Holy shit. Anyway, yeah, I don't know if there's much else to say. So again, it just really has to do with, the fact that the water molecule obviously loves to be connected to each other, which means there's a tension between the molecules. Molecules stick to each other. There's glue. And certain frequencies will break the glue, and certain frequencies will just wobble the glue. And that's really the difference. And when you really hit them hard, then they start moving in other directions. The energy gets converted. And once you've converted it into some other dimension, then it's going to be a lot harder to get rid of it.
It's pulling on that water molecule. As the water molecule starts vibrating back and forth, it absorbs the energy of the photon, and that's how the heating process takes place. Again, it's due to the quantized nature of photons that the photons are absorbed one by one as they cause the oscillation.
Right. So it's really got to be understood that when the things are when the water is in a small group, it's obviously can move around a lot faster than when it's in a big group, and so that's all really happens. You take water that's clumping, borging, and you add this energy, you start breaking pieces, you start breaking the clumps. The clumps don't fly off at some huge speed, they just break. All right, and then as you break them further and further into smaller and smaller pieces, but you keep adding energy to them, you're breaking them into smaller and smaller clumps.
to occur inside the food, and as the oscillation begins to really build up, as photons are being imparted into the food will heat up, and that's how energy is transferred from the microwaves into the food, and that's how that works.
So again, I would say that the bigger term to take away from it is dispersion. The idea is the energy comes in and it's not transmitted through the substance. It ends up dispersing, traveling in other directions than the straight line. If it travels in a straight line, it's not going to do much damage, but if it starts going sideways, the motion, that's when all kinds of trouble for the Borg happens. Alright, so we'll jump to the next one, and I think it might be here. Let's see, forward. Sorry about the commercials.
Start your year off on the right foot. Go to Wix.com and create your professional website today.
Oh, why don't I go to Square, whatever it is?
What
Square
could you
One.
do with a metal 3D
three
printer?
commercials. That's really getting
Introducing
bad.
the Metal X. The
Welcome to Electron Line.
I mean, the guy has a regular job, right? I mean, come on. Commercials for what? A couple of bucks? Sheesh. Anyway. Yeah, just Alright, so let's see what this is.
Now we're going to talk about photons in the light of carbon dioxide atmospheric energy absorption. It's a big topic in the news these days and all in the classrooms and about science. And to understand this a little bit better, I want...
This is sort of annoying because he's almost being a climate change denier. Alright, CO2 is just one of a lot of gases that can create some greenhouse effect. And water's the worst. Water's the best thing. You get water into the atmosphere, it does this microwave thing, breaks into smaller pieces, moves in all kinds of directions, hard to get rid of it. Once you get the movement into the water molecule, it's hard to get rid of it because it's moving in all dimensions. So water's really good greenhouse gas. But sort of the point would be, even though carbon dioxide is a marginal greenhouse gas in that it only absorbs, deflects, however you want to say it, diffuses energy, in very small bands. The point is always once you've heated, once you create a hotter environment, water molecules are more likely to be in the atmosphere. So the warmer you make the atmosphere, the more water the atmosphere holds, and therefore the more greenhouse effect the water will have. So you can't just measure CO2 independently and say, oh, it's a tiny little fraction of the problem, when the CO2 creates the atmosphere that allows the water to be the atmosphere to be warm enough for the water molecules to get into the atmosphere. So anything that makes the atmosphere warmer is going to make more water, and water is the primary greenhouse causer. Right? Well, that's not, it's not a complex argument, right? Yeah, it's not too complex. So you can sort of understand that even a marginal gas, a little extra of it, is going to change the balance and make it so more water's in the atmosphere, which will make it warmer, which will make there more water in the atmosphere, and that's where it gets out of control. I mean, any extra you add adds more water, which adds more greenhouse effect. So it's just the idea that it's sort of spirals.
I'm going to do a few presentations on the association with photons and carbon dioxide energy absorption. So a carbon dioxide molecule is what we call a linear molecule. It has one carbon in the middle and two oxygens on the end. So it's a linear molecule. It has what we call three ways in which it can absorb energy by absorbing energy and causing vibrations to occur, natural vibrations, in three different ways. One of those vibrations is called the bending vibration. The other one is called the symmetric stretching vibration, and the other one is called the asymmetric stretching vibration.
So we don't get any details on how they deduced this about the molecule. I would argue that it's like any other molecule. It sort of likes to be in pairs more than it likes to be a single molecule, I think, which means that it's, lining up like one molecule this way, one molecule this way, and they're sticking to each other. And that's why there's different frequencies that it ends up absorbing or spinning or turning because of. So this also gets to this argument that these part of motion, or part of the energy, can be in the fact that the molecule is actually rotating. Its rotational speed can be a way of storing movement, because now when it hits something, it's going to hit it with like its hydrogen end first, or some other kind of, its electron end, or some, whatever the, it's so I'm just saying, it's stuff that's happening between electrons and protons, and then there's stuff happening between those arrangements of electron and protons, and the fact that those arrangements can have a shape, and the fact is you can spin that shape, and that's rotational speed can be converted into a bump into something else that causes movement.
The bending vibrations when the molecule bends like this, the symmetric stretching vibrations when the molecule vibrates like this, and finally the asymmetric stretching is when the molecule vibrates like this. Each of those vibrations occurs at different frequencies, and because of that, it can only absorb photons of a very specific wavelength and a very specific frequency.
I would argue that those motions, especially certain ones of them, are really momentum, and it's just a description of the fact that you can create these little momentum engines by putting energy in. You move the electron away from the proton moves towards the electron, which means when the electron is pulled back, there's a shorter distance to get back to its neutral state, okay, and then it continues in that manner. So it's this inchworm kind of effect that the momentum isn't in the atom doesn't move in with a consistent rate. It moves in jerks based on the fact that the electron is really jerking between the pressure of the proton and whatever force hit it.
And so the three are one that has 641.49 wavelengths per centimeter, the other one is 1373 wavelengths per centimeter, and the third one is 2438.1 wavelengths per centimeter, which then translates in wavelengths of 50.
So they're just sort of doublings, which sort of indicates that it's got to be, I think, a little more complicated than that. The doubling would sort of almost indicate that there are two molecules, but whatever. But since we don't really have any background for all of this, gets into a lot of chemistry more than physics, I think.
15.589 micrometers, 7.283 micrometers, and 4.102 micrometers. So what does that mean? Well, the Earth will radiate energy away back into space, and the carbon dioxide in
It would be better if you just kept it in nanometers, right? So he's saying something like 4,000 nanometers and 5,000 or 640 would be, that's micrometers, he said, right? So that would be 6,000 something something. So this is all infrared radiation, essentially.
the atmosphere is able to absorb only those specific frequencies, and of course, not those exact numbers. You have to realize that the amount of energy absorption is in a range around those frequencies. For example, the one that's most effective of keeping energy from escaping back to space is the bending vibration, which has the greatest effect in carbon dioxide absorbing energy from the Earth, and it occurs at wavelengths of 15.
So I would argue that that's because that's the single carbon monoxide moving versus pairs moving. So yes, it's easier to move a single.
589 micrometers, but you have to realize that it pretty well absorbs energy somewhere between 15 micrometers and 16 micrometers in wavelength. And so there's a range. Of course, it's most effective at this particular frequency, but it kind of tapers off about a range of 1 micrometer in range there. Now, what about the symmetric stretching? Well, it turns out it's not very effective in absorbing energy from photon absorption coming back from the Earth. And of course, the energy coming back from the Earth is infrared radiation, IR radiation, which of course has wavelengths of greater than 700 nanometers all the way up into the micrometer range, which is what we have right here. Now, the asymmetric stretch.
So the idea is that the radiation coming from the sun is higher end, mostly visible and ultraviolet. And so it transmits through the molecules in the atmosphere, and then the infrared coming back is the one that gets dispersed and trapped.
Stretching is also a very good way in absorbing energy, but it does so at 4 micrometers, and that kind of puts it at the edge of the amount of radiation coming back from the Earth. Here's a picture that shows you the rough radiation band, radiation curve of energy going back from the Earth back into space. And notice that where carbon dioxide absorbs energy is between 15 and 16 micrometers and around the 4.1 micrometer, which is associated with these two particular vibration techniques or vibration modes. One is the bending mode and the other one is the asymmetric stretching mode. Remember, the symmetric stretching doesn't really absorb that much energy. Notice that because carbon dioxide can absorb this band and this band, there's virtually no radiation going back into space right here and right here in this window. Notice that the blue here is the radiation that's being held back by the...
And so he's sort of arguing there are saturation points where you have more than enough, say, water or CO2 in the atmosphere, and you're blocking all of one form of radiation and essentially trapping it. You know, it's stuck for too long a period of time, that you can't see any of it from space. So it wouldn't matter if you put more water in the atmosphere over a certain amount, theoretically, because you're already trapping all the radiation. Now, I don't think that drawing is true. I don't think the Earth now is H2O saturated, the atmosphere. And I would argue that, like in the Jurassic, there was a lot more moisture in the atmosphere, and that's why it was a lot warmer. And I think there was also a lot more carbon molecules in the atmosphere, and that's why it was warmer. And the carbon got sunk as coal and oil, and we're putting that back into the atmosphere, meaning we're going to put it back to the Jurassic, which was whatever, 10 degrees Celsius warmer or something.
Water vapor in the atmosphere. It turns out that water vapor is way better at absorbing energy from the Earth and keeping it from going back into space than carbon dioxide. Water vapor is responsible for about 90% of the what we call greenhouse effect in the atmosphere.
All right, so it's sort of interesting, right? Because we know carbon dioxide can be frozen like water, and we don't say carbon dioxide vapor. You know, nobody says that, but they say water vapor. Just interesting. I mean, you know, it's a little bit untechnical, some of this vocabulary that people use.
And carbon dioxide is responsible for about 10%, roughly speaking. So it turns out if there were no water vapor in the atmosphere and there were no carbon dioxide in the atmosphere, the Earth's temperature on average would be about 2 degrees below zero. No, that would be Fahrenheit degrees. Let me go back. That would be about minus 19 degrees centigrade. So with no greenhouse gases in the atmosphere. And of course, the two primary greenhouse gases is water vapor, H2O vapor, and carbon dioxide, CO2 gas.
So it'd still be pretty warm, considering, and that's because of gravity, okay, frankly, heating the Earth from the inside out.
Without those two greenhouse gases, the average temperature in the world, would be about minus 19 degrees centigrade. That's about 33 degrees centigrade colder than it is today. Because the average temperature in the world today is around...
Yeah, it doesn't sound like a huge amount considering how much atmosphere there does appear to be and all that. You'd think it would hold more than that. And the surface, you know, I guess the surface is holding energy also, trapping heat. So, yeah, I wonder how fast it would get cold going down, or whether it would have to get warmer. It would always have to be warmer than going down.
15 degrees centigrade, so minus 19 to 15 is about 34. So the number is about 33, which is what they typically use. Now, how much of that is due to water vapor and how much of that is due to carbon dioxide? It turns out about 30 degrees of that is due to water vapor and about 3 degrees of that is due to carbon dioxide. So the question then is, well, what happens when we put more carbon dioxide into the atmosphere? And the problem here is that since carbon dioxide and water vapor, because notice that there's an overlap here between water vapor and carbon dioxide, since carbon dioxide and water
So that's the interesting
vapor
thing.
already
The overlap is a sideways line, which seems kind of strange. So water vapor gets less effective as you go into the ranges where carbon dioxide is more effective. And so there's a tiny little sliver that's really all carbon dioxide.
Absorbs pretty well 100% of this energy band, and over here with water vapor and carbon dioxide, 100% of that energy band. Increasing carbon dioxide in the atmosphere wouldn't really make a lot of difference in absorbing more energy from the Earth. This here is what we call the radiation window. If this radiation window were to be closed up, of course, the Earth would heat up tremendously and all life on the Earth would probably cease to exist. But it turns out this window here, this radiation window, which allows radiation to escape back into space from the Earth, cannot be absorbed by any other gases in the atmosphere. Notice there's a small amount in that window here that's absorbed by ozone and oxygen.
Right. Well, he just said no others, and then then he says ozone and oxygen. So obviously, if you increase the amount of oxygen in the atmosphere, we're also going to get more greenhouse effect. And again, I'd say this is incorrect that we are already at saturation. So he's essentially saying we're already saturated. So it doesn't matter how much more carbon dioxide we put in because we're at the saturation level, which means we're already absorbing all of the energy at those wavelengths. And I don't think that's true.
And the rest is absorbed to the right and to the left, and this main band here gets back into space. And so the temperature in the world is pretty well regulated by these natural phenomena, by the ability and the inability of these gases in the atmosphere to absorb energy. So you see that the way this is done again, radiation coming in from the Earth, in this case it's bubbling back up from the Earth, hits these carbon dioxide molecules. When the energy is absorbed, it causes the bending, the symmetric stretching, and the asymmetric stretching, which absorbs energy from the Earth, but only in those very...
It exchanges the movement. The way to say it, it causes the molecules to move, and the movement has to be dissipated over time, and that's heat.
Narrow frequency bands, which are illustrated right over here. So you can see that. Now, what would happen if you were to double the carbon dioxide in the atmosphere? Well, we know that the split between the absorption and temperature difference, it's about 30 degrees warmer because of water vapor and about 3 degrees warmer because of the carbon dioxide. So this is caused by the water vapor and this is caused by the carbon dioxide. Now, what would happen if we were to increase the carbon dioxide? Well, doubling, let's say, the carbon dioxide in the atmosphere wouldn't do much to the amount of energy absorbed because the energy is already almost completely absorbed right here in this band. This band would get a little bit wider because what would happen here is, of course, by putting more carbon dioxide in the atmosphere, you would get a wider distribution of the amount of absorption here, and so it would cause the temperature to go up just a little bit. Estimation probably is, if you double carbon dioxide, that the amount of temperature increase would be maybe another 0.3 or 0.4.
Okay, and I would just argue that, well, you can say that, but I mean, the evidence is that we have doubled the amount, and that the temperature change was more than that. So, I don't know. Just ignore what we do know about the history? Okay, go ahead.
Some degrees centigrade, and so it wouldn't really make that much of a difference in here. It's very interesting how the specific energy absorption by the carbon dioxide molecule is really set scientifically in how it can bend and how it can stretch and how it can vibrate. So it's really locked into only absorbing those specific frequencies and not the other ones. So as long as we keep this window open and there's nothing in the atmosphere that would close this at this point, we will still continue to radiate energy back into space, and the temperature on the Earth should be fairly normal, fairly...
I just think that's a little bit of an oversimplification. There's lots of other kinds of carbon-based molecules like methane and other things that likely absorb different frequencies with some efficiency, blah, 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 blah. But anyway.
Constant the way it is. There's other factors, of course, that affect the climate a lot more, but of course that's into the climate science and not into the scientific physics science of the whole matter here. So hopefully that gives you a much better idea.
The same thing, really. Climate science, physics, same thing, blah, blah, blah.
Of how what happens in the atmosphere is really tied again to the fact that we have photons that are reaching back up from the Earth, back into space, and those that cannot make it out is what keep the atmosphere warm, and those that get back into space is what keeps the climate controlled within the atmosphere and on the Earth. And again, it's simply...
I mean, the better simplification would be to say, yes, it's about the water in the atmosphere. More water, the hotter the surface gets.
The ability of the carbon dioxide molecule to absorb energies at those specific frequencies and not the other ones. And that's how that works.
Okay.
Your business idea needs a web.
All right, well, anyway, I guess that's enough. I'll have to do. So, till the next time and such, so forth and whatnot.